Can you share your screen?
Yes, thank you very much. I'll try to do that. Can everybody see my screen and hear me?
Yes. So our third talk is Jakob Moritz from Cornell, and he's going to tell us about hierarchies and flux superpotentials.
Yes, thank you very much. And thanks to the organizers for going through with this and having this conference despite the troubled times. It means a lot to me that it's still happening, and of course that I get to present some work here. So I would like to tell you about hierarchies and flux superpotentials. And the main point of this talk is simple to state. I will present to you a new method to generate type 2b flux vacua with exponentially small flux superpotentials, which is needed in KKLT, and which moreover will simplify the search for vacua dramatically. And this is based on this paper of last December with Mehmet Demirtas, Menki Kim, and Leah McCluster. Now, before I start, I want to put out a quick disclaimer. As many of you know, KKLT requires many things. So one of those things is to find a vacuum in complex structure and dilaton modular space that features an exponentially small superpotential that I call W0. And the story doesn't stop there. Once that is done, many other things have to be done. One has to exhibit a suitable confining 7-brane configuration, such that all the Keller moduli stabilize in a controlled regime. Ideally, one would want to stabilize near a conifold to engineer suitably hierarchical uplifts to the zitter, for instance, via anti-D3 branes. Then one has to demonstrate the metastability of this configuration against all possible decays, and one has to check the assumptions that went into the previous steps. Finally, one would like to understand the 4-dimensional supergravity solutions in terms of a 10-dimensional one. And all of these things have been studied extensively, and they are complicated in part. However, I'm going to talk about only the first step, finding a vacuum with exponentially small superpotential. And this is a swampland endeavor, and sort of pictorially speaking, here's a snapshot of the swampland of effective field theories that cannot be realized in string theory, and the landscape of those that can be realized in string theory, and a large intermediate region where we don't know where it belongs. And not long ago, I think the question if a very small W0 can be realized was in this unexplored land. So the main thing I want to prove to you today is that this has changed a little bit. We now know that small W0 is in the landscape. But before I start explaining the details of that, I want to take the opportunity to advertise another piece of sort of landscaping work that I did with Federico Carta and Alexander Westphal. And what we did is we've created the first essentially complete database of O3 or 7 orientifolds of the complete intersection claviers. And those contain more than 2 million orientifolds, which, it goes without saying, provides a rich set of n equals to 1 effective field theory data. For instance, D3 tadpoles, number of moduli, number of O-planes, which we've computed. And I very much hope that this will find its way into swampland debates as well as model building. Furthermore, there's some interesting things going on there. There are sort of cool geometric transitions that we observe in there. And also a host of models of ultralight throat axions, which is a sort of model that we proposed in this paper with Arthur Hebeker, Sascha Leonhardt, and Alexander Westphal. And it turns out that these can be readily found within this landscape. So I'm very happy about this work, but I'm not going to talk about it. So if you're interested in any of these points, please check it out. Okay, the outline of the talk is very simple. The bulk of the talk is going to be devoted to demonstrating to you that the existence of flux vacua with exponentially small W0 in the landscape. In the later stages of the talk, I would like to comment on the stabilization of Keller moduli in our class of vacua, which I promise will include a new twist. And I would also like to comment on the abundance of our vacua in the landscape. And both of these terms are, both of these subjects are a little bit more speculative than the previous one, the first one. The first because K-modular stabilization is just notoriously difficult. And the second because it's ongoing work with the same authors, plus another student, Andreas Tasken. But although this is still ongoing, I would still like to show you some glimpses of what's happening. Now, unfortunately, due to this crisis, my two student collaborators, Mehmet Demirtas and Maggie Kim, don't get the opportunity to show their work. So I would also like to take a brief moment to highlight the importance of their role in this work. It's been a real privilege to work with them, and it still is. And both of them will be applying this fall. So if you're interested in hiring excellent postdocs, you should consider them. Let's start. First, to set up notation, let me give you a quick look at KKLT in a nutshell. So, of course, we consider type 2b string theory on a weakly coupled O3-O7 Calabi-Yau rentifold that I will call X. And then three-form fluxes are known to induce a scalar potential for the complex structure moduli U and the dilaton tau via the famous Gukow-Pfeffer-Witten superpotential, which takes this form here. It can be written as an integral over the 10-dimensional fluxes times the holomorphic three-form omega, which depends on the complex structure moduli, and can conveniently be written as a contraction of the flux integers f and h with the period vector pi. Now, given what I'll call a quasi-vacuum, where the f terms of the dilaton and the complex structure moduli vanish, we may integrate out these fields, provided their masses are in fact sufficiently large. And this point will be important in later stages. Now, the effective field theory that's valid below their mass scale still features the H11 plus light Kähler moduli that I'll denote by capital T, and a superpotential of this form. The leading classical term W naught is the expectation value or the vacuum value of the Gukow-Pfeffer-Witten superpotential. And there's an infinite series of exponential corrections in the Kähler moduli that in particular lead to a non-trivial potential for these fields. Interaction expansion, as usual, gives rise to a Dan-Steinbeck problem, which very roughly speaking states that if all these coefficients, W naught and the one-loop Pfaffians A, are all of order 1, then vacuum solutions to the TF term equations will hide strong coupling with the Einstein frame volumes of 4 cycles are of order 1. And this is, of course, a problem because we have no way to confirm such solutions. If, however, when we're able to find flux vacua where this leading classical term, W naught, is exponentially small, one will find instead controlled SUSY vacua, SUSY ADS vacua, with a potential of this form, with a minimum at moderately large values of T. Namely, the volumes are large logarithmically in 1 over W naught. This is these are the famous KKLT SUSY vacua. Now, it is obvious from the formula, for this to be a reasonably controlled thing to do, one needs exponentially small W naught. And so it would seem that the computational control that we buy by tuning W naught very small comes at a tremendous price of non-genericity. And finally, although I will not talk about this part at all, the KKLT ADS vacua are, of course, the starting point for uplifting to de Sitter. Now, how small do we expect on general grounds to be able to make this number W naught? Well, the classical flux counting arguments by Ashok and Douglas and Denef and Douglas, which operate in the continuous flux approximation, suggest that it is indeed possible to tune the flux superpotential down to very small values, which are of order 1 of the root of the number of total vacua. Now, due to the enormous abundance of such flux vacua, this would imply that W naught is basically an arbitrarily tunable parameter. However, we could be beware of such arguments, because the whole point, in a sense, of the swamplet program is that such arguments can sometimes unexpectedly fail. And unfortunately, brute force checking of the above scaling down to very small W0 isn't feasible in practice. And it turns out that despite the development of innovative directed searches, vacua with small W0 remain elusive. So brute force checking is, of course, not the best thing that has been tried, but so far, no examples with very small W0 have been reported. For one of those methods were covered by Alex's talk. Now, this state of the literature has led to the following situation. There are these opposing expectations that one can have, which are all sort of justifiable. On the one hand, one might think that there exists a swamplet criterion that tells you that, in fact, W0 is bounded from below by some order 1 number. If that were true, one would have to prove this. On the other hand, one might take the flux counting arguments at face value and assume that W0 is effectively arbitrarily tunable. And I think this is a sort of insufferable status quo, because much depends on it. In particular, the KKLT de Sitter vacua, and with it much, although of course not all, of string model building are built on the assumption that W0 is a tunable parameter. So this is just something that has to be checked. Moreover, the possibility that the Sitter vacua actually don't exist in string theory is a real one. So, and the question of small W0 is thus, so the question if the small W0 can be realized is important for arguing whether or not the Sitter vacua exists in string theory. And finally, even the supersymmetric ADS vacua one starts with are interesting. Namely, they feature scale separation between the ADS length and the Kaluza-Klein length. So these form possible counterexamples to the sort of no scale separation conjecture. So let's start. Let me tell you how to construct vacua with exponentially small superpotentials. So what we're going to do is we're going to consider the large complex structure patch of a complex structure moduli space, which is the mirror dual of the large volume regime. There, the complex structure moduli U appear in the superpotential through the period vector pi in an integral basis of cycles, which is itself determined from a prepotential, which I'll call F. And this prepotential is given by a sum of two terms. One is a cubic polynomial, and the rest is an infinite series of exponential corrections. And this entire prepotential is essentially determined from geometrical data of the mirror dual Calabi-Yau X tilde. Now, a general idea that we're going to pursue is this. One judiciously approximates the superpotential in terms of some approximation plus a remainder, and instead solves the approximate F-term conditions plus the exact vanishing plus the approximate vanishing of the superpotential itself at some value u. So these equations, these are more equations than there are moduli. So in order to find such solutions, one has to sort of align the approximation scheme with the input data of fluxes. In the next step, one searches for nearby solutions where u is the solution we found here plus some small offset of the full F-term equations. Then it follows that if the approximation was good in the first place, the vacuum value of the superpotential W0 will be small. And this is a general scheme proposed by these authors long ago. Now, our strategy will to go along these lines. What we're going to do is we're going to approximate the superpotential by only considering the polynomial piece in the prepotential, so neglecting all exponential corrections. Then it follows that that the superpotential one finds will be exponentially small at large complex structure. So that's a bit of a quick argument because one also has to show that we can actually make these fields U somewhat large. But I will show this. Now here's the sufficient condition for existence of a solution to the approximate F-term conditions plus the approximate vanishing of the superpotential. One considers two integer vectors m and k, which both have as many components as there are complex structure moduli, such that a vector p that one defines via m and k, as well as the triple dissection numbers of the mirror dual, which is a rational vector, one demands that this lies inside the calicone of the mirror dual Calabi-Yau x tilde. Furthermore, we're going to ask that this vector p is orthogonal to the input vector k. And one also asks for a suitable quantization condition that I will not give any details about. In this case, one can show that integral flux choices of this form, where f is determined by m. I've left some things blank here, but these are determined in a straightforward linear map from m. And h is determined by k. It turns out that this choice leads to the solution where this approximate will the approximate f terms as well as the superpotential will vanish exactly. However, along an entire one-dimensional locus where our complex structure moduli U are proportional to some constant vector p, which is the vector p that is defined here, times the axodilaton. And such curves of vacua we've dubbed perturbatively flat vacua. Now, it's important to note, of course, that this means that by doing so, we stabilize all but one of the complex structure moduli and the dilaton at the polynomial level. So the scalar potential would then take the following form. There's a flat value that we can parameterize by the axodilaton. And there are the orthogonal directions which are heavy. Now, how do we stabilize this remaining flat direction? Well, we still have the exponential corrections to the superpotential. So, in other words, the effective superpotential along the flat value parameterized by tau is now given by this expression in terms of the flux numbers and the instantonic part of the prepotential. And it's a sum of different exponentials with coefficients in the exponent p1, pq, etc., which are rational numbers determined by the choice of fluxes. The prefactors, particularly h and the remaining ones, are in turn determined by Gupa-Kumar-Waffer invariants and fluxes. Now, importantly, this superpotential here takes the form of a racetrack superpotential, where all parameters that show up here are computable. And this will turn out to allow modular stabilization at large values of the complex structure moduli and the dilaton. And if that's the case, which I'll show that it is, the vacuum values of the superpotential one finds turn out to be exponentially small indeed. Now, let me show you how this works in a concrete example. I'm going to consider basically everyone's second favorite Calabi-Yau, the degree 18 surface in weighted projective space 11169, which has 2 Kähler moduli and 272 complex structure moduli. Now I'm going to employ a technical trick. We know that its mirror is defined by the resolution of the orbifold of this Calabi-Yau via this discrete group Z6 times C18, which is basically just the result of Green and Plesser. So it follows that the Z6 times Z18 invariant locus of the full large dimensional, like 272 dimensional complex structure modular space is actually just a 2-dimensional one. And it is identical to the 2-dimensional complex structure modular space of its mirror. In particular, this means that the symmetric periods are just those of the mirror. Then it follows that if we choose to turn on only fluxes that preserve this symmetry, by virtue of the unbroken symmetry, if we solve all the f-terms equations along the symmetric locus in modular space, we are guaranteed to actually solve all the 272 f-terms. So what is the input data that we get from this model? So the mirror dual of this Calabi-Yau has triple intersection numbers that are given by this expression here. And the leading genus 0 Gupa-Kummer-Waffe invariants are 540 and 3. And note the order 100 hierarchy here. That will be important. Now, it's easy to confirm that this choice of fluxes M and K will give rise to a perturbatively flat vacuum where the complex structure moduli U are proportional to the axodilaton with proportionality constant P, which is the vector of fractions 2/5 and 3/10. And the effective superpotential along the flat valley takes this form. It's now the sum of two exponentials plus subleading corrections, where the coefficients are just those of the vector P. And the prefactor H here is the somewhat hierarchical number 5/288. Now, there are two crucial properties that I'd like to note about the superpotential. First, the two coefficients here, P1 and P2, are slightly detuned in the sense that their relative difference is a quarter. Furthermore, the prefactors, so H and suitable normalization 1, are hierarchical. And these two factors together allow one to indeed stabilize a recoupling. Namely, the expectation value of e to the 2 pi tau will be given by exponentiating this hierarchy factor H by 10, which is the inverse of P1 minus P2. And W naught will be given by the hierarchy factor H exponentiated by the inverse of this, so by 4. And this gives rise to a superpotential that is of order 10 to the minus 8, which I think is quite remarkable given that the previous records were of the order of a few percent. Now, we're not done yet to prove that this actually exists, because we still need an O3 or 7 orentifold that will support our vacuum. And here is one such vacuum. We consider inverting the fifth coordinate of 11169 of the weighted projective space with weights 11169. And this leads to two non-intersecting O7 planes, as was studied extensively in this nice paper here. And none of the moduli are projected out. So H1 plus and H1 minus are both 0. Now, in this situation, there's a D7 brane tadpole, of course, to DD07 planes, which can be cancelled by placing 47 branes on each O7 plane. In this particular instance, we get a gauge algebra SO8 times SO8, and the curvature-induced D3 brane charge on the 7 branes is given by minus 138. Now, our fluxes have positive D3 brane charge, which can be easily computed to be 124. And that, luckily, is smaller than 138, so the remainder of the tadpole can be cancelled by including mobile D3 branes and a combination of Wolf volume fluxes on the 7 branes. And this completes the proof. We found a vacuum where W naught is as small as 10 to the minus 8, so we've proven that such vacua are indeed in the landscape. And this is sort of the main result I wanted to show in this talk. But now let me go beyond. Of course, just having shown the existence of one vacuum is not enough. What we want is to be able to systematically search for vacua of the kind that I talked about. And first of all, the construction I've laid out features, I think, very intriguing relation. First, and this relation is between the hierarchies we find in flux superpotentials and the hierarchies that one finds in Gupa-Kummer-Waffe invariants. So, after having learned how to apply the classic methods developed by Hosono, Clem, Tyson, and Yau to actually compute these invariants for general Calabi-Yau hypersurfaces, which have, for instance, larger values of H21, non-substitutional Morricone, and other things, one may then search systematically for such hierarchies. That's the first part. And the second part is I haven't really given you many details of what are the conditions, what's the form of the conditions that give rise to such a perturbatively flat vacuum. Most of these conditions are just trivial, and because they imply setting certain flux integers to 0. But one of them is not trivial, computationally speaking. Namely, we have to solve a homogeneous Diophantine equation of by degree h1 minus 1, 2. In other words, the vacua will correspond to rational points in this hypersurface in a product of projective space. And the reason that this shows up was this constraint that our vector of coefficients in the exponentials has to be orthogonal to the flux vector k. This gives rise to this equation. Now, the existence of a solution to a generic Diophantine equation is a classic undecidable problem. But in practice, this isn't such a big problem. We can still efficiently find solutions. And what I'd like to show you, and this is preliminary work, so please take it with a grain of salt, are all the vacua where the flux vector m sits inside a range of -40 to 40. And the Calabi-Yau I'm going to consider is a different one, which has 3 complex structure moduli and 181 Kähler moduli. And what I'm going to show you, and part I'm showing it already, is the number of vacua here on the y-axis. And on the x-axis, I'm going to show you the inverse of log 1 over W0. So this is the control parameter that sets the value of Einstein frame volumes, what their inverse. So when this is small, KKLT is well controlled. And I'm going to start with all the vacua one finds by restricting the overall D3 band charge in the fluxes to be less or equal to 50. And now I'm going to incrementally increase the D3 band tadpole to see how the structure, how the distribution of vacua that we find changes as we see new vacua popping up. So let's do this. So at 100, of course, we find more vacua, and one notes that smaller values of this control parameter start to appear. And this keeps on going. And what appears to be true is that the distribution that one finds doesn't really change as we increase the cutoff tadpole. So I'm going to increase this up to 450, and I hope it's been sort of clear that the distribution itself hasn't much changed. And by doing this, one finds in the last steps, one finds vacua with W0 as small as 10 to the minus 30. So this is a bit preliminary. For this Calabi-Yau, I'm not going to show you an orentifold that actually has such a large tadpole. But the point that I'm trying to make with this is a different one. Namely, it appears to us at this stage that the distribution of vacua one finds isn't sensitive to the tadpole bound itself. Of course, it still remains true that granting larger D3 band tadpoles does give rise to smaller values of W0, but at this stage it appears to us, and this is a bit preliminary, so just want to be clear about that. So it appears to us that this is only due to the larger sample size one gets for obvious reasons by increasing the tadpole. Now, let me comment on something different. Namely, what remains on our way to stabilize all of the moduli. So the most pressing issue, I think, is this. On the complex structure side, we have stabilized explicitly 2 of the 272 moduli and demonstrated that this is an actual vacuum. But one would like to know what is the full Hessian matrix that includes also the 270 symmetry breaking directions. And we are working on this problem. But I'm not going to tell you anything more about it now. Moreover, one would like to stabilize all the 7 brane moduli. This I consider not an insurmountable problem, given that at least for this particular orentifold that we've been employing, 7-brane configurations have been studied very extensively in this nice paper. And in particular, configurations have been found where indeed all the 7-brane are still. Then there is and that's perhaps the most pressing and the sort of the newest aspect. There's a single flat direction that we've chosen to parameterize by the axolotl, which has a mass scale of order W0, which is of the same order as the mass scale of Kähler moduli. And this is a general feature of these sort of vacua. We can't get rid of it, so we have to deal with this. And this is where I'm going to tell you about a new twist on, and this forms the new twist on Kähler moduli stabilization. But I want to give you a little bit more details. If we assume that only this one field in the complex structure modular sector is light, then after including also the Kähler moduli, we get an effective superpotential of this form. This is the racetrack superpotential that I wrote down before. And we also get exponentially suppressed corrections in the Kähler moduli T. And n, and I've included also fractional numbers n here, 1 over n here, where n are the dual Coxeter numbers of confining gauge theories on 7. Now, at first glance, nothing much changes. You can convince yourself that the stabilization of the dilaton and the Kähler moduli proceeds as usual, of course, assuming that these numbers here are not vanishing, which ensures control over the string loop expansion and the expansion in the 12th coupling of the gauge theories. However, controlling the alpha prime corrections in the Kähler potential becomes more difficult. Now, the reason is that the string frame volume of 4 cycles is given by 4 pi over g Young Mills squared of the 7-brane gauge theories times gs. So the factor of log W naught here just cancels out, and the only enhancement factor we get here comes from the dual Coxeter numbers of confining gauge theories on 7-branes. In other words, the alpha prime expansion now becomes a 1 over n expansion, and W naught has dropped out of this problem. And whether or not one can actually engineer such gauge theories with large enough n to ensure control remains to be seen. So let me conclude. So the main point I hope I have conveyed is that we found a new class of vacua at large complex structure and small string coupling, and we've described how to explore it efficiently. Now within this class, exponentially small flux superpotentials are readily found, and the preliminary findings of a more broader search that we've initiated suggest that these vacua start to dominate over the generic ones once you make W naught much smaller than 1 over n. Now the KKLT moduli stabilization scheme within this class comes with new challenges. The sort of obvious one, the presence of the light field, and the less obvious one is that the alpha prime expansion now requires large n. In particular, ET3-brane instantons don't seem to work for this particular model. So I think these results could be a significant step forward in establishing the SUSY ADS vacua of KKLT. However, of course, the quest for KKLT to 0 vacua lies ahead of this. And that's all I wanted to say. So thanks for listening.
Thank you. Okay, so we have one question in the chat window already from Severin.
Hi, yeah, thanks, Jakob. This is actually very cool. You commented on the 7-brane moduli and said that you are not particularly worried about them, right? For example, in the explicit example which you presented where the very first one, do you know that you can stabilize the 7 moduli within the tuple bound? Can you explicitly do that?
So they have presented explicit models of sort of large rank gauge theories where this appears to be possible. So they show that the deformation moduli are frozen by this. And the tadpole, the remainder of the flux tadpole that one, so this can be done within the tadpole bound. But then the question is, does that leave enough space to actually still lift this vacuum that I've presented? Now, as far as I remember, the vacuum that they give, this turns out to be not the case. But there exist other vacua of the same form with slightly bigger W naught, something like 10 to the minus 4, that do fit into this. So I'm very hopeful that this can actually be done completely. Yeah.
Okay, cool.
Okay, do we have other questions? Yes, Aaron Palti.
Hello.
Hey,
thanks for the nice talk. It's very nice work. So I just have a question about so the slight direction that you get is because you have to turn off the cubic terms because of the Euler character alpha prime cube parameter is not a rational number.
Yes.
Right.
Yes.
So, but have you thought about doing the same thing but taking a Calabi-Yau with a vanishing Euler number? Because then that vanishes, and then you can take rational. Everything is rational, so you could do the same trick.
Yeah, that's a great suggestion. So in this,
yeah, and then you wouldn't have this flat direction.
Well, so this particular so one of the cool things about this way of constructing vacuum is that you can just solve algebraic constraints in flux numbers themselves involving triple intersection numbers, and you can explicitly just derive what is the solution corresponding to this, without actually having to start solving the differential equations again. But I mean the v prime equal to 0. I'm not sure. So one thing you can do is do the same thing for a cubic superpotential, where the rational term doesn't appear. Maybe one can do something similar for a more generic one where it's cubic plus quadratic, so it's not homogeneous anymore. I don't know if one can do such a thing, but maybe.
Thank you.
Okay, we have another question from Michele Ciccoli.
Yes, hi Jakob, thanks for the talk. So in the last case where you had H11 very large, did you think about the interplay with what Cody has talked about a few days ago? Because he was saying that when you go to large H11, in order to trust your effective theory to have all cycles larger than 1 in string units, you will need to go to large volumes.
Yes.
So would that mean that your W0 would need to be extremely small, 1? And 2, what would be the mass of these moduli? Would they be extremely light so that everything will be ruled out cosmologically? Or from fifth force bounds even?
Excellent question. So first of all, if you talk about the perturbative alpha prime corrections, then as I briefly showed on the last slide, is that W0 itself doesn't have much to do with it anymore, but instead the dual Coxeter numbers of the gauge theories, and they can't be made too large. So it would be very interesting to see if there was this interesting work by my collaborators and Cody, who showed that at large H1 the calicone is very slim, very narrow, which is why you get such large volumes once you ask for control of the alpha prime expansion. It would be very interesting to see if one can do KKLT in these large H1 models, and I don't know the answer. But something we can often do here is to use the Green-Plesser construction to map models with large H11 and small H21 to the inverse, and then stabilize in compact structure modular space along a symmetric locus. So yeah, but yeah.
Thank you.
Thanks. I don't see any other questions. No. Okay. So let's thank Jakob again.